So please allow me to introduce our guest lecturer today in the session, Dr. Norhasliza from University of Malaya. You have met her yesterday. Dr. Norhasliza, for the question, is it the participant can interrupt you?
Yes, sure. They can interrupt me.
Okay, if you have any question during the lecture, you can raise your hands. And I encourage you to turn on your camera during the questions so that we can see your cheerful face. So everyone, please give a warm welcome to Dr. Norhasliza.
Right, thank you, Dr. Laki. Okay, hello everyone. Is everyone okay this afternoon?
Yes, we are okay.
Yeah, okay. So how about the student? Do you manage to do the exercise yesterday? Or still trying to figure out how to do the tutorial? Oops, can you give me permission for screen sharing?
Okay, wait a moment. So you are now.
Okay, I can share now.
Okay.
Right, thank you. So I can see that there were only 47 participants now. So not everyone is coming yet in this afternoon session. So for this session, we will make it short and then we just go directly to the tutorial that I've prepared previously, and you can take it from either from the GitHub or the Google Drive provided by the organizer. Okay, let me hold on. So there will be two files today. There is Introduction to Regression, and another one is the tutorial of Introduction to Regression. Okay, so I think that most of you have listened to the lecture this morning, and you have already an idea how to do regression and also what does the regression mean, right? So you can see that there is both what I call the interpretation between from Eric and also from Tree is a bit what they call, although it's the same, but how they treated the regression definition is what they call it. They have their different way. Okay, so I can see that in the morning from Eric presentation, he more focuses on the what we call a scalar based what they call it numbering. So it's just a very straightforward how to deal from the what we call it mathematics, and also the how they interpreted from the theorem or the what they call it a lemma, the one that they took from the statistical book. And you can see the another lecture after that from 3 is he introduced a more like a vector like what we call it how to treat the regression, and from there you can see that he deal with a lot of parameters, especially when he deal with the partial differential what we call it equation in all his matrices. So he deal with a lot of what we call it different variable. At least there are two variables that treated in the matrices, and from there he will do reduction according to what are the problem that we want to learn. Okay, so for today, actually the one that I'm introducing to you today is the basic one. Is taken from the textbook Introduction to Regression. And why I choose this one, because I want you to, for those who never do regression before, at least you have idea what does the regression means, and also how we treated the regression, both from the what we call it mathematical side, and also how we treat it when we have what we call some equation or data. Okay, so let us move to the what we call it a bit explanation. So when we speak about regression, let you have seen in the today's lecture from this morning, most of the regression, they call it an astronomer, whenever it doesn't care about the order. Anything the polynomial is considered from what they call it the first order or the higher order, they still treat it as a linear regression. But in maths or in physics, they don't say that, right? So it's depend on what are the field of your what they call your research or your work. The definition might be differ from one to another. Okay, it depends on what we call it, what the area that you are working now, and they will define the definition. Okay, so here linear regression is actually an attempt when we want to model a relationship based on the linear equation to the observed data. So I think this is you have learned in your undergraduate course or during your high school, how we can, when we have a set of data and then we want to find, for example, the best straight line. This is the most basic one that you have learned during your undergraduate or during your first, during your high school. Okay, so when we do experiment and everything, we have some X and Y data, and then we are trying to find what they call the best fit. So the most common things that we use for the fitting for the what they call it data, what we call as a least square method. Okay, so least square method is the simplest method to do for the linear regression. So when we speak about least square method that I mentioned before, it calculates the best fitting for the observed data, and from there we have to how to get what we call it. The result is we minimizing the sum of the square for all your vertical line, and after that you have, and it must be what we call cross at 0. Okay, at what they call it your y0, it will cross there, and from there you can get your what we call it the best fit. Okay, so I move on to the next one. So I'm sure that you have seen this equation before. For example, this is the common one if you find in the textbooks, how to get the linear what they call relationship between these two variables of x and y. Okay, so the idea is you have the m as your what we call it gradient, and your b is your y-axis intercept. Okay, so this is the most what I call common thing. So if you have some example here, like this equation, you can easily what we call it interpret your equation into your linear equation. And if, for example, when we have data here, all this bar here is what we call as error bar. Okay, so when we do what we call it observation or measurement, there must be error. You will get the error bar from your calculation. Okay, so that's why when we try to fit the data, doesn't matter what's method, either you want to do least square method or regression, it must fall between this error bar. So if you, for example, in machine learning or artificial intelligence, sometimes they try to, what they call it, if you have a lot of scattered data, like you have seen the data, the talk this morning, you have a lot of scattered data. And sometimes when you do the normal linear least square method or linear regression, they don't cross all this data. So what the idea of machine learning is, they try to what we call do the more, what they call it, more variable, more complicated regression, so that all the point will be taken care of. Okay, so that is the idea of machine learning. So if you do machine learning or artificial intelligence, the basis idea is still coming from the what they call it the normal polynomial, because that is the way people do it 100 years ago, and from there the knowledge is expand towards what are our current understanding. Okay, so here when we have a least square method, for example, the normal one, if you have y and x are linearly related to a straight data, what is the best fit for our estimated data or observation data. Okay, so in order for us to find the best fit is to find best estimate of your gradient and also your intercept. And this is what we call as a linear or least square fit for the straight line. So when we speak about what we call it, this how to fit data and how to get the best fit, you have to remember that these are only estimate. It is not the real result. No matter how good is your computational is, they still have, because this is estimate, anything related to the computational or any what we call it method we use, no matter how complicated or how sophisticated the algorithm will you created, they still just an estimate, right? It's not actual, what we call it the best result, because how to constrain our estimate is based on our error analysis. Okay, so this is just the equation that I'm sure that most of you have seen, this least square method, how we deduce from the summation of the value of x, and also this is our gradient. And this is why we say that if you have a negative or positive in the end, it will override each other to get the least square method. Okay, and uncertainty in measurement for the y value, this can be given by this formulation. Okay, so this is, we get the, what they call it, the uncertainty of measurement. And from there, we can see that how much the error either is fall between our error bar or not. Okay, so here also we can estimate uncertainty for our gradient and also our intercept. And this is just what we call the standard deviation that we can get. And from there, we can estimate. So maybe you have learned this during your, what they call it, experimental lab in your first year or during your high school. You do some measurement and then you have to tabulate all the errors and see that whether it's fall between your, what we call it, the measured error. Okay, and then we're going to see that what is the how good it is. Okay, so how good, so you also must hear about this this morning. And usually for the least square method, we use what they call it R square, what they call it method. This is what we call as the goodness of the fit. This is also known as a chi-square. So here, it's like how good is your, what they call it, fitting. It lies between 0 until 1. So if your R square is 1, it means that you fit nicely, everything fall between your points. And if you have a 0, it means that your fitting is poorly behaved. Okay, so this is one thing that you will see how does the behavior of your least square method, right? So when it says it's between 0 until 1, so differently, this is probability. So because just like the probability or the statistic, you can get what they call in between 0 and 1. Okay, so usually you get, it's seldom you get 1, you get, for example, 0.99 or 0.998, depending how good of your fitting. So when we test the, what we call it, the least square method, for example, we test for one, or what they call it, fitting, and see that how we can adjust the parameter so that it will fall between the best fit. Okay, so this is an example. This is just, I'm taking this from my lecture. Okay, so because I'm teaching a physics department, so we have some Hooke's law, and then we have some measurement of mass and also some, what they call the length of the spring. And from there, when we, what we call it, measure, do some experimental in the lab, we can have this, we change the, what we call it, the mass, and then we see that how the length will be elongated or it will expand. Okay, so from there you can tabulate the what we call it result. Okay, so from there you can analyze the data. Just you can try your own. This is just the sample of the calculation, and from there you can. So when I teach the undergraduate for the numerical method, first I will ask them to create least square method directly from this formulation, because I want to teach them to do coding, right? So because although in Python, all those things already available, you can just call the library. but because the idea when I teach the class for undergraduate, I want them to have some experience in do all this messy, what we call it summation. It's just an exercise. So, but why? Because I want them to test either their how they write the code, and also when we call the library, how much the different or how good is the one that called by the library, and also the one that the student write themselves the code. Okay, so they will see that how good is what we call it if you use directly or by using library. Okay, so this is up to you, either you want to do it or not, but we can focus directly to what are the library Python will call this one. Hold on. So in a Python, there are a package called SciPy. Okay, so SciPy statistic is where it will calculate the linear regression for the value of x and y, and then it will calculate automatically the gradient and also the intercept in the equation, and from there you can directly feed the data. Okay, so it is quite straightforward. You don't have to do the equation, right? So it's just calling and then feed the data. And okay, so I'm not sure that I give this code or not, but later on you can see. And next, I'm moving to the polynomial regression. So this is when we have the one that we see just now. It's just the what they call it the first order. Okay, so what happens if you have higher than first order? So we have what we call as a polynomial regression. So from what I heard this morning, it seems that astronomer or astrostatistics, they just care that it doesn't matter how many orders is it, it's still considered as a linear regression. Okay, so when we have a polynomial order n, this is being expanded by the Taylor expansion. Okay, so we have when we expand our calculation by using Taylor expansion, it means that we are creating more what they call it coefficient and also variable to define our polynomial. Okay, so we can have a quadratic, linear, or we can have a cubic. It depends on whether we want. So if you have, for example, this one, I don't explain about cubic spline. Cubic spline is another method to do the regression, and this is needs more sophisticated understanding because you have to create a coefficient for the B spline, right? So can we do the polynomial regression to fit a polynomial equation? Yes, we can. It's quite easy. And can we do linear regression on the data to fit polynomial equation? Yes, you can do it also, but the simple linear regression might not give the data, the fitting might not be very good. Okay. So we move on to the polynomial regression. Again, Python do have their own library. This is, you can use NumPy polyfit. NumPy polyfit calling if you have x and y data, and then you have to give what are the degree or the order that you want to put. Okay, so others is actually just non-compulsory. If you have to put some, for example, condition, either you have a convolution or not, so it will try to fit nicely. Okay, so if you have a fit polynomial for certain function, okay, so for a certain degree, so you just have to assign what are the degree or the orders that you want to do for the fitting. Okay, so if you are going to another one, the library that widely used for the polynomial regression is what we call as poly1D, and this is also called by NumPy, and this is to get a polynomial from the coefficient generated by the polyfit. Okay, so this is just polynomial fit, the normal one. It's quite what is the difference between this one? Actually, this one is the simplest one, and this one is we can cater for certain order of degree or the n orders. Yeah. Okay, so this is the first one. I have another tutorial to show it to you. So this is, I put a bit explanation, but this is in the PDF Word document. Okay, so this is, you can try afterward for during the breakout room after this. How to make this one a bit. Okay, doesn't matter. I hope you can see it. Okay, so we have what we call it, you can try to do for the least square method. This is quite simple for those who don't have any experience in programming or still struggling to learn Python. You can start by testing the exercise number 1, where you are given a data. I think the CSV file is already available in your, what we call it, in the GitHub. In the GitHub, okay, so you can download it, and from there you are going to read by using pandas to how to read these 2 variables, and then you call what we call it the SciPy least square method, and you see that how it fit the data. Okay, so this is quite simple to do. And the next one is we are going to do for the supervised learning regression. Okay, so from here we are going to describe both linear and polynomial regression. This is also taken from the lecture that we are teaching here in but this is quite a basic one. It's not really what we call it the complicated one. They're just the basic idea, because this is undergraduate level. Okay, so from here it's just that we are going to find what are the, how to use a special library to do this supervised linear learning regression. Okay, so we have, for example, some data set for the variable x and y, and then we want to apply a simple regression to find the best fit, will be denoted by a function fx. Okay, so we have y equivalent to yx, and then from there we can, if we have more variable, we can do for example multiple linear regression. Okay, so if we have order 1, definitely we have a simple what we call it equation for your polynomial order 1, and from there we can try to, what they call it, plot or do linear regression, and from there we have to understand how the code works. Okay, so I provide some algorithm for you to read, and also I'm going to explain a bit how the linear regression algorithm being used in this exercise. Okay, so first we are going to have to import the library from the Python package. This one is already, if you install Anaconda or if you use Google Colabs, everything is there. You don't really have to worry about that. We are going to use standard one, NumPy, Pandas, and Matplotlib, and then we are going to use a scikit-learn. Okay, I don't use TensorFlow or Crust. It will be explained by other lecture in the next few days, right? So from here, I'm using whatever available in the package. No additional, what we call it, installation is required. Okay, so when you have this or this library, and then we can generate a data set, because I don't have any data to give you exercise, so I generate the data from some random sample generator. And what happened is Python is very good in creating this random data set. Okay, you call NumPy random, and it will create a random data set for you to play around. And it is also can be used in your exercise yesterday for the Monte Carlo. So Monte Carlo is you generate some random number, and then we try to find the, what we call it, the integral for the certain range that we constrain. Okay, so from here we generate some random data set to set for the linear regression, and from there the random is we create as a noise. Okay, because this is artificial data, we want to test it, right? So from there we can use some linear regression within the scikit-learn to create a model, and then from there we can create some coefficient. What is coefficient? If you see the formulation, for example, A0 and A1 is your coefficient, Y and X is your what we call it, your data. Okay, so from there when we want to fit the regression, okay, like this, if you have what we call multiple linear regression, and you can have, this is all your coefficient that we are going to calculate. So the scikit-learn will find what is the best coefficient for you to fit your data. because your data is that you have two values, right? You have y and x, two what you call variable, and these are the coefficient that it will create to make your data as a best fit. Okay, so when you have this all those polynomial, so you can, for example, here is the step that you can try. The code is already given. You can try later on. So you are given a code, a linear regression.py, and from there you are going to generate for 100 data set for 100 size with the x single variable by giving this formulation. So it means that you have this coefficient we created, y equivalent to x plus y plus noise. Noise is we created from the random number generator from NumPy, and then you will, when you create the function, you call the user-defined function, and then you can create the set of what they call it data. Okay, so from there, from the code, you call the linear regression, and then to fit the models, and after that you will find what is the coefficient, and then you will get the plot. Okay, so let me show you the code for this one. Hold on. This one is in Python, in the native Python. I don't convert into the notebook, but you can load it in the Jupyter notebook, no problem. Okay, it will recognize it. Hold on. So I'm going to share the whole screen. Is it? Okay, I hope you can see it, right? So this code is, oh sorry, this is my work. Okay, hold on. Okay, so this is the code that I provided in the GitHub account, and also you can, this is in a native Python, and that's why you can see that this is .py instead of IPYNB, the interactive Python, but you still can load it in the Jupyter notebook, no problem, and you will read it as a Jupyter notebook later on. Okay, so what happened now, you can see that I import several, what we call it, library. So I import a NumPy, I import scikit-learn. This is already available in your, what they call it, Python package, and also I import some matplotlib. Right, so here is the three, what we call it, pandas is if you have data set or you have some astronomy data set, you can import either pandas or astropy depending on your usage. Okay, so this is, I just create artificial data for this exercise. Okay, so here we are going to generate some random data set. So from here, I generate some hundreds of data. Okay, so one thing I want to mention to all of you, depending on your machine, start creating a random data set from the smallest, I mean, not smallest, from the small scale. 100 is still okay. So you can test it if, for example, if you have a lower end machine or 2 gig, for example, don't create 1,000 or 1 million random number. It will crash your computer because Python use a lot of memory, okay, to generate this random data. Because I experienced this when I teach a student, that when they start to increase the number of random generator, 100 means that you create 100 data, 100 points. If you say 1,000 points, it will create 1,000 points. If you say 1 million, it will create 1 million points. So all this data will be what's called generated by your computer. Okay, it will generate randomly, and then it will store in certain temporary place in your machine. So if you have a slow computer, it will crash everything. Okay, so this is one thing that you have to remember. Unless you have a powerful 16 core, what they call, or you are running towards server. So I don't worry about that. So if you just run to your local machine, mean that your own laptop or your own personal computer, please carefully do this. All right. So after that, we're going to call, this is the random generator from NumPy. So here we create some data set, And why I put this one? So if, for example, if you want to have more than you want to change the parameter, you can just change here instead of you put somewhere else. Okay, so here we assign some X observation, some random uniform of the low is 0 until high is 200 value, and the size of your random is around 100. Okay, so what does the random uniform means? It means that it will slice up the value of your random number evenly. This is what we call uniform. They also have a non-uniform random generator, means that your data, one data and two, the first and second data, the size is a bit different. This is, we get the same size. Okay, and after that, we have also some, if you want to create some random noise, we can create some NumPy random noise. Okay, so this is just how we scale the value. And now we have our formulation here. This is from question number 2. Okay, so this is the function that we are going to solve. Okay, so I have to edit a bit. This is, I'm taking from a longer tutorial. This is, I cut it short for this exercise. All right, so here we're going to set the value of what is the, this is the, our, what they call it, the data set of X, and also this is our data set of Y. So you can see that I created by using this formulation, and X is coming from the shape of the random value. Okay, so from there we can call a linear regression. This is coming from the scikit-learn. You can see that the scikit-learn is here, linear regression. It will call it directly, and from there we can do the coefficient fit for the linear regression to fit the X and Y data. So when you fit the data, you will find that if you want to check, so this one, this is just for checking. Okay, so if you don't really care about what is the value, it doesn't matter, because this is, I want to see what are the value of coefficient of A0 and A1. Okay, so from here we can see that what is the coefficient and also what is the intercept that fall in the what they call regression. Okay, so, and this is just a cosmetic for the plotting, where I want to have a figure that have a size, the frame size is 10 times 8. If you want to have a squarish, you can do 10 by 10 or 4 by 4, depending on what are the preferred display. And also this is just a title. And after that, we can plot the result, and you get, this is, what is this? This is a marker how we want to get the point in the plot, right? So from there we can, this is also just to show the grid in the, because I don't use Seaborn. If you use Seaborn, it can do automatically the grid for you. Okay, and after that you can see that what are the result. Okay, so this is the this how to get for the your fitting and the data. And after that, you can predict the linear regression by using the second method. And here we create some array of value, and from there we call another what we call it, linear equation, and we predict the shape for the regression. So from there you can compare your result, this method 1 and method 2, and see that what is the best fit for your data. Okay, so you should get something like this when you run. Hold on, where is my another finder? Oh, this is. Let me see. I have a lot of file here. You should get, if you can run and you can get, I don't run it, so at least I want to show you how does it look like. So the plot name is linear regression.png. or it doesn't want to show yet. So it doesn't matter. Let me stop sharing first. I'm going to open my. Any questions so far? Let me run this code and show you the result.
Yeah, while waiting, yeah, maybe we can have a question session. So here we have Alia. Yes, please, Alia.
Thank you very much. I'd like to ask for in the Python file that the X is being reshaped. Yeah. Why do we reshape the X? Yeah, thank you. I still don't understand it. Thank you.
Okay, so let me see. We reshape. Okay, so this is the reshape function. Let me share the screen back again. While waiting the code to compile. Okay, sorry, this one. Okay, so here, because you can see that I do this reshape. This is because we create the data randomly. Okay, so here we want to shape the what we call it, the data. This is data coming from the number, what they call it, the random generator. This is random. Means that the Python will create you some what they call it, some value of a random number, and after that we are going to, because Python must read the data in array. Okay, so in array, so we want to get what is the value of because we don't know what is the shape of this random generator. Okay, so what we did is we have to reshape the numpy to a matrix. Okay, by using this reshape function. Okay, and this is as I mentioned, this one in this code is required for this package. That's why you have to do that. If not, they will give error. So because scikit-learn only can understand the what they call it, the matrix, the data that you have in terms of matrices. For example, if you call data from a file from .dat or whatever, you have to make sure your data is fall between in terms of array. So we have to define. That's why I'm not sure for AstroPy, but Pandas will automatically reshape the data for you. Maybe those who are using AstroPy know better than me. So if, for example, if you have some data from ASCII data or any free format, so Pandas will immediately create the array for you. Okay, so like this one, because this number is just some random number, so we have to give the shape for the scikit-learn to know what is the what called the array for the calculation, right? So that's why I can see that the value of -1 is number of error for the original random number, and value of 1 is for the column of for the original. It means that we have only 2 columns because we have X and Y. Okay, so this is how we do this. So if you want to see how does it behave, okay, so you can print, for example, print this X orbit. You see how the data behave, and then you print again X and see that how the data will change. So from there you will understand. Okay, so this is the trick how to know the behavior of the data. Okay, so this is from the output from this code. So you can see that these are the random number that we generated from the equation, and this straight line is actually your what we call it, your linear regression coming from this scikit-learn. Okay. Any other question?
Any other question?
Anyone still have problem in using Python? Because yesterday I have forgot to ask any of you. So everyone already, because this is when you run the code, this will be what you call saved in your directory. Any question?
Yeah, ma'am, am I audible?
Yes. May I know who's talking now?
Yeah, ma'am. This Shubham.
Yeah. Please,
Okay.
Ma'am, can you tell this noise line like np.random normal? Like I know the uniform one, like it will produce numbers from in between 0 to 200, right? Total number of hundreds, but how this is working, this np.random or normal?
What is the difference you mean compared to the random normal and also random uniform, you mean?
Yeah, man. Uniform, I understand.
Oh, okay. So random normal is how to say it? Is what we call it. This is another random generator that we're going to have some data. Here you can see that we put it start from 0 and then it will scale until what they call 5, and you can see that when you can print the noise and you can compare what are the difference between these two. Okay,
Yeah,
so
ma'am.
this, yeah,
That's why I asked. Like I printed noise and I got like negative numbers as well in that, so that's why I asked.
oh, okay. So when you have this random, you have to, I also have to check what is the definition. So here is the random normal. They just want to create some what we call it, some additional data that what we call it, similar to noise. You know, noise, it means that it can be the data that not really fit into this our data, not data, what we call it, the actual value that we want to generate. So it will give you a non-uniform data compared to this one. This one is we constrain. This one is not constrained. It will give you a normal random value that generated from your computer. That's why you have negative as well.
Okay, so what this scale is doing? Scale equals to 5.
Scale, let me see. I think, hold on here. And then here we just want to have some scale. Let me see. I have to print result. I have done this for quite a long time. I have to remember. Okay, so let me see. Okay, hold on. Let me close my file first. It will create a lot of data after this. Okay, so right, so I see that. Let me see the library first. Okay, oops. Okay, so from here you can see that I printed the random normal data. Okay, so for this what I call exercise. So random normal is actually we are going to get, this is sample from the Gaussian distribution. Okay, so when you have this Gaussian distribution, when I see the data, then I can see. So you have the Gaussian distribution is a curve, right? So you have from a negative to the positive scale, right? So it will scale from the scale, the what we call it, the standard scale is 1. If you scale 1, it means that from -1 until, but this one you can see that the random number generator, it create until also -12, negative, let me see, -1. And this one is the scale to get the standard deviation for the Gaussian distribution. So this is just some random value. Okay, so you can check the NumPy, what they call it, documentation that I've given to you, and in the slide, and to see that the actual definition, how we want to do the location. The location here, I put here 5. Location is 0. Scale to 5 is we're going to find what is the size of your what we call it, the shape for the what they call random number generator itself. So there is you can put, if you want to test one, you see that how does it behave in the plotting later on. Okay, give a try and see how does it behave.
Yes.
Anything else?
Thank you.
Yeah, no problem. So the one that I've shown you just now is totally in scalar. It's not a vectorized yet. Yeah. So if you want to do vectorized, you have to manipulate a bit your equation here. Oh, I can see there's a question. Raise hand.
Esanuli, please, you can ask your question.
Hi, am I audible?
Yeah.
Okay. I was asking that in numpy.polyfit, do we need to always enter the degree, or is there any way that numpy can figure it out from the data set on its own, or do we always need to put a polynomial degree?
Okay, it's a polynomial fit. You can see that we have there are two different. If you want to have a degree of freedom, you have to put different polynomial 1D. It will do for only a linear one. If you want to have a certain degree, you have to what you call it, put what is the degree of your fit. Because why? If linear, you have to remember. So if linear is a straight line, right? So if you have or the higher order, your plot won't be a straight line. Okay, so that is a different one. So if you have sample code for so if you want to do this degree, so if the what they call it, the standard one is the linear, is don't have any zero, only n equivalent to 1. So if you don't put any degree, so it will consider just a straight line. So if you want to have more accurate, what they call it, fitting, you just increase the degree, and you will see that how it behave later on. So it will be oscillate a bit at the in the end of your plotting because of the number of your degree, your x here. So if you have x power 3 or x power 4, it will wiggle a bit in the data later on if you see. So you can test that what they call it, the degree of freedom. So if you just don't care about degree of freedom, you just use the linear, the single, the n equivalent to 1, the linear one.
Okay, thank you.
Okay. So there is a question in the chat. Do you have sample of code that we can use vectorized or vectorized notation? You need to have some equation to explain and then do the vectorize. Okay, so that it will be a bit more what they call it, more longer equation and more longer code from this one. I think that tomorrow Tree will give you the vectorized sample code, if I'm not mistaken.
Yeah, in his hands-on.
Yeah, yes, because he will do based on his lecture.
Any other question?
So usually vectorized, what they call it, notation is we use a lot in the galaxy distribution, if I'm not mistaken, and also galaxy evolution. But if you want to use just to deduce just simple data, scalar will be more than enough to do it. Anything else?
Any other question?
No? Yes? Or still thinking how to do it? The one that I've given to you are all the very basic or very, what they call it, simple way to understand this linear regression, because this is the organizer asked me to start the flow from simple, and then after that, when the lecture progress, you will start to have more and more complicated, what they call it, method for you to learn to use that can be used for your work later on. Anything, you can ask also the one that we discussed yesterday, no problem. We can mix both of the question session because this is my last lecture, if I'm not mistaken.
Yeah, so take this advantage. You can ask Dr. Liza as much as you like.
So this is your last chance to ask. Anything else? Okay, so whenever all those either the what they call it or the library call in the NumPy or in SciPy or in scikit-learn, these are built based on equation. So you have to remember that it's not just purely you get as is it. All the library is actually being behind the library there are equation being written that. So from there you have to understand what the equation are before you included all the what they call it parameter or the value that you want to run for your particular problem. Okay. Anything else? For everyone still sleepy because this is afternoon session. For
Okay.
everyone, yeah. If not, maybe we can move to the breakout room. Betul lagi?
Okay, so since there's no more question, maybe the participants are shy or they would like to ask the question in the more private room, in the breakout room. So
yes, sure.
yes, so now you can all go to the breakout room. Okay, welcome back, Dr. Liza.
Yeah. Yeah, we're going around to the breakout room, have chat with people there.
Okay, so we will have some discussion, Dr. Liza.
Yeah, let's see that everyone is here. So may I know what is the progress so far from all the students? You're okay? Or
Okay,
still?
here we have Chandra. We have Chandra who raised his hand. Please,
Yes.
Chandra.
I'd like to ask one question.
Mm-hmm.
In the polyregression.py,
Yes.
in line 120, there's zip. What this do? What is it mean, zip? And also I see this variable x2 and y2 has different size, array size. X2 has two columns and y2 has one column. Why this not cause an error in lr.fit?
Hold on. Is a polyregression or linear regression? Linear regression.
Polyregression.
Okay. Regression. Hold on. Let me open the file. This line
120.
120. Let me see.
The zip. What it do? What it does?
Oh, okay. So right. Hold on. I'm opening too many code. Let me minimize all this thing. Okay, so from here, you mentioned that this array of, we want to list zip for our, what they call it, the data here. Okay, so why we did all this thing? So this is the step 5 of linear regression, right? So when we test for the step 2, because this is already put some nice exercise. So step 2 and until step 4, you can see that here we generate the random number and then we try to fit. And after that, we do some prediction by using 2 methods for the linear regression. Okay. So after that, we find that if the regression does not fit well, okay, so then we going to what they call it, combine the value. So that's why you can see that we have to create some array, list of this random number, and then we have to create another what we call it, the term for this is for the n1 and this is for the n2. Okay, so you can see that we have two terms in our equation, right? So this is another test because the one that we test before is purely linear. Linear means n. In what I meant by linear here is the n is order 1. Okay, so here we increase the order. So that's why we have what they call it different size now, right? So when we want to set the higher order, so then we can test another regression and then we again feed the data. So that's why you will get two plot, right? When you test for this two plot or one plot, let me see. Okay, only one plot from this one. So this one we want to see that either the matching point of our result will fit nicely in the data. Did you manage to see what are the different if you test the first and the second one?
Yes, ma'am. What? Pardon?
Did you see that what is the difference when the result from the first method, the method until this one, and after that we increase the what they call the order for the array?
Oh yeah, I see that.
Okay, so this one, the idea is because we want to have higher order, that's why we create the another array for this one. Okay, so this is we want to do what they call it the higher order approximation. So if you want to do, for example, x power 3, so we have to add one more term to do for the fitting. Okay, so that's why, because each polynomial, they need to have new coefficient. So this is how we create it for each random value.
I still don't understand about LR2.fit. X2, variable X2 has 2 columns and Y2 has only 1. Why it don't cause error?
The size, you mean?
Yeah, the size.
Because this is the value. Okay, so you have to remember why we put LR2, because we don't want to have if you put LR, this is just the rename. Okay, because if you put LR, it means that it will override the one that we have done before. So because we want to save it, so we put LR2. Now we still feed X and Y data. The data still two value. The only difference is the polynomial term. This is one thing you have to understand. All right, so the data still two set, but the polynomial can be increased because of we have P0 plus P1 plus P2. This is a polynomial to fit the point. Okay, so when we have this all this what called the data here, this is just to create the coefficient for each x, because when we want to create coefficient, where is the coefficient come from? It must come from when we want, if you learn maths, the Taylor expansion. So when we have a y equivalent to whatever x, the x in the end, it will sum up into the point that we want to plot, right? So that's why here they fit your x value. Okay, so this your x, this still have 2 columns. It won't have 3 or 4 columns. If you want to have that one, so you have to print what is the coefficient for each one of them. Okay, so this is just to get the what they call it, this one they call to fit the x and y value that we want to fit. So if you print this one, obviously you get 1x2 and y2, because now the x and 2 is different from the original of our x here. Okay, so because we have to increase the coefficient. Okay, so if yeah, you have to write down the equation, because I don't put some equation here, so it come from there.
Okay, thank you very much.
All right, anything? So how's because I think we're going to wrap up soon, so may I know what is what they call the progress, or do you find it is from easy to hard, how does it it goes? I think the one that I give for this today is the basic part of the machine learning and also the introduction to Python. Later on, when the school progress, you'll see that much complicated code and much, what we call it, more vectorized term will be introduced later on. So this one, I try to put the basis understanding for you to understand, although it's not that easy if you don't really have, because I don't put the maths behind it. So usually we have to learn the maths behind it and transform into the code. But here, because it's only 2 sessions, everything be reduced or diluted a bit. So usually I give this lecture for 5 weeks for this type kind of topic, especially for those students who don't have any background on this thing.
Yes, we really have a really limited time and we complete everything. So but you can still have some discussion in Slack, right?
Yes,
Dr.
correct.
Yes. So
Yeah,
if
yeah,
you
no
have
problem.
more question or something to discuss, you can also post your question in Slack. Okay, we already at 3 a.m.
Yes.
So maybe if you still have some question for Dr. Liza, you can also post it in Slack, right?
Mm-hmm.
Okay.
Yes. So is
Okay.
everyone okay? So I cannot see. I think everyone is still trying to run the code, I guess. So
Dr.
shall
Liza,
we? Sorry.
can you turn off the share screen maybe?
Okay.
So that
Yes.
we can see
Yeah.
everybody. Okay. Right. So is it okay we close the session?
Yeah, it's okay for me.
Okay, so thank you very much, Dr. Liza. Very interesting talk. Very, I believe that this is very useful, hands-on for all the students here. So I want to encourage everyone to turn on your camera, show your cheerful face, and please give a big applause to Dr. Liza.
Okay. Well, thank you. I want to thank especially to Iqbal and all the organizer, and also Dr. Laki for inviting me to attend this school. It's very interesting to get new people and also get in touch back with old friends. I think part of I already met people from the committee, and I hope all the students could gain at least some knowledge from my lecture, at least 10% or something for those who really clueless, but for those who are more advanced, I guess that you're able to do most of the code. Thank you again, everyone. And if you have any questions, so I'm still available in Slack, so don't be shy if you want to ask anything. I'll see you again soon, perhaps after COVID or something like that. All right. Thank you, everyone.
Thank you very much, Dr.
Thank you very
Liza.
much, Liza.
Yeah, thank you.
Thank you very much, everyone, for your